electric field that is happening in this molecule. That is the first concept. But Raman spectra, if you want to get the Raman spectra of this XY molecule, then this is not enough. The molecule possessing polarization is not enough, but this polarization has to change. And this can be changed by two ways. One way that we already discussed in the last class. One way is that this particular molecule can rotate. Rotation of this molecule, and rotation of this molecule may change the polarization. Okay. So what that means? Initially, your ellipsoid is like this. So in this direction, you have minimum polarization. This minimum polarization, and this is maximum polarization, minimum ellipsoid. So radius of ellipsoid. So this is maximum polarization, okay. And in this one is minimum polarization. Now, if you are rotating uh, that particular molecule, for example, at this angle, then your polarizability ellipsoid also will change, and you will get a different. So in this case, if you are applying electric field in the axial in this direction, so in this case, that is making an angle theta with its axis, xy axis, that is the axis. Then you may not get the polarization. Large polarization will not be there. So you will be having some polarization, but it will be less than more polarization. But in this direction, you will be getting smaller polarization. And also, if you are applying that perpendicular electric field like this, I'm talking about on that surface. But this is actually a three-dimensional system, so you cannot exactly. I'm talking about this rotation of this molecule in this field. So it is not your object plane. So that you have to keep in mind. So in this plane, I am talking about. So rotation is like. So now what will happen if you are considering this angle theta? So this perpendicular, if you are applying electrical perpendicular, also that also makes theta to this. So the polarization, there will be some polarization because it is not 90. So there will be some polarization which is larger than the first piece. So this is your first piece, for example, your first piece, and this is your second piece. So here polarization when you are having that perpendicular electricity. Similarly, this one also. Then, your ellipsoid will be having some kind of. So your polarization, if you are comparing with the initial one, now what will happen? You are applying that perpendicular, you are getting some theta angle. It is not exactly. So it will obviously having more polarization as compared to this one. So it will be having lesser radius. So radius. Similarly, as compared to the previous one, along the axis, or if you are considering this direction, along this direction, in that case also it is not along the axis, so the polarization will get reduced, so that this particular radius will get increased because polarization. So we will get somewhat flat. So you'll be getting confused. So in this direction it will increase, in this direction it will decrease. Okay? So you'll get something like this, it will be less than this one. Direction less than, but in this direction it will be large because from there. So that's about this polarizability story. And what happens here is that when you are rotating that molecule, the polarization is getting changed. So the rotation of that molecule will make changes in polarization. So a change in polarization is necessary for Raman study. So only that if the molecule possesses this condition, then only the Raman. Okay, so that is first case. So we already said that uh, a change in polarization is necessary. A change in polarization, change in polarization can be rotation of molecule possesses polarization that direction. In some cases, we will not be getting this change in polarization if the molecule does not have any polarization. Suppose if the molecule is not having any kind of polarization initially, then that kind of molecule sometimes it will not. But it also depends on what kind of operation that is. For example, if you consider the carbon dioxide molecule, so in this case, moment of inertia on both sides will be cancelled. So even if you are applying some electric field to this particular molecule, so both in both sides we can have, for example, if you are applying electric field in this direction, or if you are applying electric field in this direction, so this will not affect. So it depends. It depends on that molecule also. It also depends on the axis. For example, if you are considering here for the carbon dioxide molecule, where it will not affect because this will ignore this direction. If you are considering only that axial direction, the direction if you consider for this carbon dioxide, then that will not change because both sides we have that polarization and polarization in the opposite direction, and that will dipole moment, and that will cancel each other. So in that direction we will not get any polarization. And if you are rotating such molecule which will having any kind of polarization, that will not be damaged. But in this case, if you are considering the vibration, so there is another possibility. This is not the whole story about so if the molecule which is possessing as zero dipole moment with some particular direction, that will not be active. Similarly, if the molecule does not having any kind of change in polarization, even if you are rotating in case of some molecule, if you are rotating that, it will not give you. So, for example, we can also consider a symmetric molecule like e-educat or something like that. So, in that case, also we have this kind of symmetry. And if you are considering that along this axis, if you are considering the molecule is rotating like this, okay, so with respect to this axis, for example. With respect to this axis Z, if the molecule is rotating, then that will not produce any change in the polarization. Even if you are applying and if you are getting some polarization in this part, but if you are rotating that on with respect to that z axis, for example, yeah. So in that case, it will not be going to affect the polarization. That kind of rotation will not affect because these atoms, let's say this is CH3, so these atoms are symmetric, and whatever moment of inertia that you are having along with that these atoms, that will be same. So there will not be any kind of polarization change in this molecule when you rotate this molecule about this. So with respect to that axis, the polarization will not change. But if you are considering this end over end rotation, like all this H is coming up, L is going down, in that case, polarization will change. So because polarization along this direction will not be equal to polarization along this one. That will be different. Also, the angle where you are having that will also change. And so, in this kind of a molecule, in some axis, if you are considering, this along that axis also will not be getting any polarization. So, in that axis, Raman will be inactive. Okay, so we have to consider all these things. Also, if you are considering that vibration, that is also another story. I think we already discussed that in the last class about that stretching vibrations, how the polarization change this polarization ellipsoid. How it is. Okay, basically, we are plotting this as with respect to that alpha. Okay? That's why this is called as polarizability ellipsoid. And if you are considering this vibration case also, if you are having those vibrations in the last class, I think we have discussed with the water molecule. So for that water molecule, we have different kind of polarizability ellipsoid with respect to its vibration. That we already discussed in the last class. So that is also possible. So a change in polarization can be achieved through rotation of the molecule as well as vibration of molecule. So vibration we are not considering that. So now we are going to deal with pure rotational Raman. So what will happen in this case if you are considering this Raman spectra or Raman spectra? If the molecule is rotating, what is actually happening? So we already studied what is the energy corresponding to this rotational levels. Uh, when we discussed about the microwave spectroscopy, also we discussed the calculation for energy of different levels of the class for rotation of the molecule. So that will be given by, so I will write here, rotational energy levels, rotational energy levels of, and we are now considering linear molecules, not considering so we have to consider a linear molecule, and we will start with the diatomic molecule or numbers of means that diatomic molecule linear pattern. So all those things we will discuss later. First, we consider the simplest case, that is nothing but the diatomic molecule. So in this case, if you are considering then the energy for different levels, the rotational energy for the case of linear molecule can be written as and this we already studied this in micrometry. So this will be given by I'm expressing in terms of epsilon j and which is in centimeter. So b into j plus 1 and then in addition to this, we have this dispersion constant. Then J square into J plus 1 square is much of centimeter. So I am representing energy in terms of centimeter. And if you want to represent that in joules, then you have to replace this E with you multiply that then you will get so we are not considering that. We are considering that in terms of centimeter inverse. And also, in the case of Raman spectra, this distortion constant will not affect much. Okay, so under that condition, I will just write it here. Raman spectroscopy. Raman spectroscopy. I will write it fast. Transition. So in Raman spectroscopy, the distortion constant does not affect much on the precision of the measure. Or simply you can write in Raman spectroscopy, the effect of distortion constant is very small, so that we can in your own words. So that implies that epsilon j equal to b into j into j. We are ignoring the constant. So we are not considering that anharmonicity and all those things. So this is the rotational energy in terms of okay. And the selection rule corresponding to this transition selection rule transition. So this is in the case of Raman spectroscopy. Selection rule for transition that H equal to 0, plus or minus. So here we do not have any plus or minus. So we have only J equal to 0, plus or minus. And if you're asking why this 0 and plus or minus 0 means there is no change in rotational energy levels. It means that whatever energy which is coming, the radiation which is coming is passing. So that is the important concept. Each of these selection rule is having some concept. So I will look on that part also. Because when you are considering delta J equal to 0, which means that the rotation, there is no rotational energy level change, which means what that means, if you are having a sample here, you are having your molecule here, your sample, and if you are sending the radiation inside this molecule, and if you are considering the radiation is giving some energy to you, or the radiation is absorbing or getting some energy from the molecule. In both those cases, we have an energy difference. Okay? So if you are giving some energy to this molecule, then the molecule will absorb that energy and rotate. Okay? And that is one possibility. And if this radiation is not going to have any interaction with this particular molecule, and then that radiation will simply come to this detector, whatever it is. Yeah. Okay. So in that case, the molecule is not going to absorb that energy, and transition will not happen. Okay? That case is delta J equal to, which means that there is no transition happening. In other words, the molecule doesn't absorb the radiation, or the molecule does not giving energy to the photon. The photon does not. So in that case, there is no rotational energy change. So that the delta J, that is the transition, the transition between delta J. So there is no transition happening. And if any radiation which is coming like that, then that will be resulting your fundamental band, as we discussed in that case in the first lecture of this program. So we had this central peak. Okay? That central peak is corresponding to whatever the radiation we have sent. Same radiation which is coming. And we called this particular band as Raman, sorry, Rayleigh scattering or Rayleigh line. So this is representing that Rayleigh line. Okay? Or we can this process nothing but Rayleigh scattering, and it is elastic scattering. Sorry, this is an elastic. And in the case of delta J equal to plus or minus 2, so this is for delta J equal to 0, and delta J equal to plus or minus 2 means that there is some transition happening. Okay? Yeah. So the radiation which is coming out will be having because of that. Okay. So delta J, which is plus or minus 2, is having another important thing, because we are not considering delta J equal to plus or minus 1 here, but we are considering delta J directly as plus or minus 2. And this is because of the symmetry. And this will give you that Raman lines. And remember that if you're considering this delta J equal to plus or minus 2, why this 2 is coming instead of plus or minus 1 is that there is a symmetry associated with all these rotations. Okay, so because of that, why it is coming. For example, if you consider an oxygen molecule, here you have an oxygen, and if you are having this kind of a rotation which is happening, this particular molecule, and this molecule will be possessing same symmetry twice in this particular rotation. And this oxygen is taking at this position, then it is coming back. So we have two stage where the molecule looks exactly the same. That is symmetry. So this kind of rotation, linear diatomic molecule, if you are considering, and if you are rotating that, then we have some symmetric kind of shape. Even if you consider the case of the different molecules also, the total polarization when you consider, that will be symmetric. So that's why we have this delta J equal to plus or minus 2, which is coming as your selection group. So in order to have that, when you are completing that rotation, the molecule will possess okay. So I'm not going to explain. This is also there in your textbook why it is coming. So this selection rule is because of the symmetry of that polarizability. So similar to that polarization. So if you are considering that polarizability ellipsoid, there will be some symmetry, and because of that, it is coming. So because of that, because of that symmetry, it possesses same appearance twice in a single rotation. Okay. So that's why we are getting this plus or minus 2. This is your in your textbook also. So that's about this delta J equal to plus or minus 2. And if you are considering the normal case, when you are having that j upper minus j lower if you are considering. So let's consider delta j equal to j upper minus j lower. This is the conventional way of writing delta j changing. And if you are considering this case, then we can ignore delta j equal to minus 2, delta j to minus 2 case, because always we consider why so this not delta j equal to minus 2 is ignored. Why this has to be ignored? Because we need in always we need in the upper state we need more mode or that particular state. The upper state quantum number, because we are ignoring this minus 2 here because the upper state quantum number is higher. So if you're considering this kind of a condition, upper state quantum number must be higher, then upper minus lower will be always positive. So then we have to consider now we have delta j equal to plus 2. And if you are drawing with this under this condition, delta j equal to plus 2, we get a different answer. And also, if you're considering the energy change in energy, delta epsilon. So remember that epsilon is the energy, and delta epsilon is change in energy between two energy levels. So this can be calculated by using this equation in epsilon with, for example, j dash is equal to j plus 2 minus epsilon with j dash. So lower state j quantum number we take it as j double dash. So I'm not going to explain all those tiny things. So understand that J dash is always upper state quantum number. J double dash is always lower state quantum number. This already we did in several times. And the upper state quantum number will be higher. Okay. And this upper state quantum number is higher by 2 in Raman because we have. And the lower state quantum number is represented by J double dash, and which will be less than from that higher quantum number. So we have only J in this. Now, if you substitute this particular condition in this equation, so I will just take this as equation number 1. So if you substitute that in 1, then you will get the energy substituting 1 in 2. That implies delta epsilon is equal to epsilon is equal to 4 b into 4 plus 4j plus. So this is a change in delta energy after substitution. So how this can be done? So I will not explain all those steps that you can do by yourself. Here I will show how it is done. So all this energy calculation, that epsilon, all those things that can be done by yourself. It's not a big deal. So just substitute those values in that particular energy equation. But you have to perform it. You have to write it down on the paper by using pen and so you have to make it. You have to derive it. Then only you can write it in your exam. Otherwise, you will not get it because all these things are very confusing. And if you are not going to write it by yourself, derive it by yourself, solve by yourself, you have to. So try to get it by yourself. Then you can. So I will just show this time. it is coming. So energy equation, I will wrote here itself. So if you are putting that in your equation number one, what will happen? Your equation number one is epsilon j equal to b into j into j. Your epsilon equal to b into j into j. Your equation one. So if you are putting epsilon j dash in that particular equation, then what will happen? So the difference you have to calculate. So that's the epsilon equal to. If you are putting epsilon with j dash equal to j plus 2, then we have to substitute b into, instead of j, we have to substitute j plus 2. Now my j is equal to j dash. Here, in this case, we are considering epsilon j dash equal to j plus 2. So all this j becomes j dash. So b into j plus 2 into j plus 2 plus 1 minus, in this case, when you consider this energy level, all my j will become j dash over energy, and which is equal to j. Okay, so all my j double dash. So in this equation, all my j will become j double dash. Again, I have to substitute instead of j double dash. So this will be j into j plus. So this will be equal to b into j plus 2 into j plus 2 plus 1. So how this will come? Plus the form from j square j into b plus 2j, j into 1. Okay. Then second term plus 2j, 2j plus 2 into 4. Okay, I can take plus 3. Okay, so and then minus b into, this will be j square plus so now b into j square is here, b into j square plus b into 2j here, so 2bj plus j. So and also we have one 2j, right? So here it is 2j, so plus. So here we have total of 5j, 5j into 5j, and plus 6 minus bj square minus uh, this one is minus j square. So now what will happen? This bj square is here. So this bj square can cancel. 5jb here. Here we have 1jb. So this will become 4jb. And plus 6 will come. You take that b constant and b into 4j plus. So this is your expression for delta epsilon. This is the change in energy between the upper and lower. So yeah, by this way, you have to do all those delta epsilon and all those calculations that we have to write for microwave as well as infrared. So otherwise, we will not get any. Anyway, so this is the change in energy between energy levels that we have. So this is the expression for that, and here one more thing is j can be taken value 0 plus 0, 1, 2, 3, etc. These are the values, and also remember very carefully that this j value is the j of of lower level or lower state. This J value is the J of lower state. Remember that, because when you are getting some problem from this section, then they will give you the transition. For example, transitions from some 2 to 0 level. You are considering 0. And in that case, if you want to select what J value, then you have to choose the lower state level J value. So remember that. In this case, in Raman have lower state energy in any transition. In all transitions, if you are considering, then you have to choose in the calculation, you have to take the lower state value. Okay, that you have to keep it in mind. And if you are considering the corresponding, for example, if the molecule is gaining energy, some cases it will gain energy, and energy of photon get decreases of this photon. And if the molecule loses energy, then the photon, this photon also will gain energy. Okay? These two are possible. So if the molecule gain energy, this we already discussed. If the molecule gain energy, which means that the photon energy gets decreased, photon energy gets decreased, and vice versa. This means that if you are having molecule which is decreasing its energy because of that scattering, then that means that photon will gain energy. So both are possible. Both that things are possible. So this energy difference can be happen in such a way that in terms of frequency, you can write it as this. This is also an example. So wave numbers of corresponding spectral lines. So if you are considering mu s bar as your spectral line, and that will be given by mu s bar is equal to mu x. This is Ex means that excitation frequency. So mu bar Ex, that is the excitation frequency. That means that whatever frequency is coming and inside on this molecule, that frequency, that is the excited frequency, which is nothing but whatever frequency which is coming out. We usually term it as exciting frequency. So that is the excitation frequency, which is nothing but the radiation which is coming and hitting on that particular molecule. Plus or minus V times plus or minus V times 4J plus 6. So whatever there is some energy change because of the rotation will be added up with the fundamental frequency, or which can be subtracted from it. Both are possible. This is with respect to whether the photon is gaining energy or the photon is reducing. So with respect to that, what kind of interaction happens? Okay. This obviously it is an inelastic collision or inelastic scattering. So because of that inelastic scattering, some energy will be exchanged by the photon to the molecule, or the photon can absorb energy from some kind of energy exchange happens with the molecule and the incoming radiation of the incoming. Okay, so that's why it is called as inelastic scattering. And because of that, the frequency may get, or the photon may get extra energy, which means that this frequency may increase. Okay, as you know, this energy. It's new. H is a constant, only mu is going to change when energy. So when the photon absorbs energy, the frequency of the incident radiation is increased. If the photon gets reduced its energy, which means that the frequency of the incoming radiation. So both these are possible in physics, and we will get along with the central line lines below and above. So that's the Raman scattering, basic Raman scattering. And because of this is because of rotation. So this is the spectral shift from the central line. Uh, how much spectral shift? V into 4j into 4j plus 6. V into 4j plus 6. Shift will be there. It can be plus or minus because of this. Okay. And if you substitute, if for example, if j equal to 0, then what will happen to this mu s bar? Why I am putting s here? Because this is s branch. This will give me s branch. Okay, because my delta j equal to plus 2. Delta j equal to plus 2 means s. Keep it in that. So this is mu bar s. S bar. So mu s bar, if you are considering if j equal to 0, if j equal to 0, uh, mu s bar will be equal to mu excitation bar. I'm putting this bar because we are taking it in because we are considering better lines. So we are not considering mu. If you are considering mu, then it is frequency. All those little details are there. So this is mu excitation bar plus or minus. If you are putting j equal to 0 here, what will happen? 4j will become 0 on, and only the 6b remains. So this will become. So what that means, if you are considering j equal to 0, then which means that you are considering the separation between the first line and the central line. Okay, and what is that separation? That separation is 6. That separation is 6. So this will give you the separation between first line and central line. So central line and first line are separated by 6. And if any value, any other value, if you put, for example, if j equal to 1, j equal to 1, what will happen? Mu s bar will become mu excitation plus or minus. If j equal to 1, what will happen? 4j will become 4 plus 6. So totally it's 10p. Come here. So this is 10p. So what is the difference between j equal to 1 line and j equal to 0 line? So this is your first line and this is your second line, right? This is your second line when j equal to 1. So in between this first and second line, what is the difference? So between uh, first and second line, separation equal to, is that separation? Separation is 10p minus 6p. 10p minus 6p. That is, I will write it here. Minus, that is 4. This you can work it again. If you want, the third one. US bar, bar plus or minus. What is that? j equal to 2. Then j here it is put j equal to 2. This will become 8. 2 into 4 is 8. 8 plus 6 is 8 plus 6 is 14. 14b will become 14b. And if you subtract these two now, because these two are adjacent lines, j equal to 2 and j equal to 1, and this will give you again 4b as separation. 14 minus 10. So this is again 4. So between first line and the central line, we have 6b separation, and in between each other lines from 0, first line, second line, third line, in between all those lines, we have 4b separation. And b is, you already know, b is the rotational quantum number. We can calculate by that equation that we will be equal to h square by 8 I this. So by using this equation, you can calculate, or from this you can get what is b. From that you can get what is I, that is moment of inertia for that particular point. And then from that you can calculate what is the average distance between that in that molecule. Similarly, if you know that intermediate distance, that is reduced mass of that molecule, from that you can calculate what is the mass of isotope that we already discussed in the. Okay, so that is the separation between each and every lines that we have to consider. And if you consider that from the figure, we can represent it of transition along with that. That will be looking like this. Now, if you consider, these are the different transitions that are possible. And you can see from here it is starting from 7 to 5. So the change, if you consider in this case, we're considering that change, then that will be 2. Change will be always 2. And here also, if you consider, it is going from 5 to 7. So every time it is taking 2 energy. That's fine. And from that energy level plus 2, sorry, from that fundamental excitation level, this is your new excitation bar, so this one, this central one. From that, the first line will be having a separation of 6b. Remember that? Will be having a separation of 6b. And that is separation between this first line and the fundamental line. And in between each other lines, for example, if you consider these two lines, will be having a separation of 4. Similarly, on the other side also, these two are having separation of 6. Okay? And all other lines will be having a separation of 6. And when you are considering mu excitation plus some mu, that is nothing but b into 4b plus 6, that equation, whatever you are getting. So if you are considering mu plus something here, let's say mu 1. So for different transition values, we will be having different. So you have to consider it as different frequencies here, not a single frequency. Because for different j value, which means that different j quantum number, rotational quantum number. Okay, this is the, for example, j plus 6. So for different j value from 0, 1, 2, etc., we have different energy, which is corresponding to different frequency of rotation. So that will give me different energy levels and different energies uh, associated with those rotations, and we'll get the different spectral lines. So that's why we are getting this kind of a spectra here with the different distinct lines that we can observe. Okay, and the intensity, maximum intensity will be corresponding to which level is highly populated. That we already discussed in the case of corresponding equation for J max, where the J value with maximum population that we already discussed. So this kind of a spectral lines which will be possible when you are having excitation plus something. Similarly, you will be having same kind of thing you are having. So you'll be having same kind of spectra on the other side. And this spectra, which is plus to new excitation bar, which are the stop lines, and these are anti-stop stop, stop, stop line. So these lines that is represented here are stops line, stops line. And the other side we have, this side we have lines which are anti-stop. Stops. And remember this stop is a name. So first, so when you write that in this anti and put this anti. So these are anti-stop lines on the left side, and on the right side we have stop. There will not be any change in the suppression. And in this particular case, this both of these are having same kind of intensity. Because all those rotational energy levels transitions are probable, and the probabilities are same. That's why we are getting same. And one more thing I have to discuss here is that because of the nuclear spin for homonuclear homonuclear nucleus, sorry, molecule, for homonuclear molecules, like oxygen, hydrogen, etc. IR and microwave, I'm writing microwave, pro, that microwave. So IR and microwave spectroscopy. This is an important point. Spectroscopy will not work, or which is oxygen and hydrogen like happens with the homonuclear molecule. Like, so which means that they will be having same same nucleus. Same nucleus on both sides. If you are consuming oxygen, you will be having two oxygen. Okay? So they'll be having same kind of. So that those kind of molecules are called as homonuclear. Okay? They are IR and microwave inactive, or we can say IR and microwave spectroscopy not working. Okay? Why this will not be active in IR or microwave? Because they do not have any kind of momentum. So they do not have any kind of dipole moment. Not dipole moment, and they do not have any kind of dipole moment, because we need both microwave and IR perspective. So this will not work as they are inactive in higher microwave spectra. Since it is in bracket, can write it in since the because they are not having equal and opposite charges. That's why oxygen is having negative one corresponding. So we cannot have equal and opposite charge. So they do not possess this dipole moment. Uh, so this molecule will not be active in IR. But these molecules are Raman active. So we can say this Raman spectroscopy. Raman spectroscopy is complementary. The Raman spectroscopy is complementary like that to IR and microwave spectroscopy. So you can also use HCPY. Anyway, so this is the point that if you are considering homonuclear molecule like oxygen, etc., so such molecule does not possess dipole moment, so they are inactive in IR and microwave spectroscopy or microscopy that IR and microwave spectra. So but if you are considering these molecules for the case of Raman spectroscopy, they will be active in Raman spectroscopy. Why? Because they have change in change in polarization. They are having that radiation. So they possess this when they and then they will be Raman active by this particular technique. Because they are inactive in IR and microwave spectroscopy, but they are active in Raman spectroscopy, which means that they will give you Raman spectra. Okay, so we can say that the Raman spectroscopy is a complementary technique with IR and microwave. They are not just like this. Raman spectroscopy is not just like IR spectroscopy or but it is a complement because some molecule we cannot study with the conventional IR or IR or microwave spectroscopy. That can be studied by using Raman like this homonuclear molecule. But it can be studied Raman because in this Raman spectroscopy we need only that polarization. Okay, so this is the basic idea behind the Raman. And one more also, one more point also, rotational Raman. So that is nothing but the spectra of molecule with the, I will not write it because it is spectra of molecule with center of symmetry. So I'm not going to write it. No? For example, if you consider oxygen molecule or carbon dioxide molecule, these molecules are possessing center of symmetry, as you can see here. We are considering carbon dioxide or carbon here. So this kind of molecule with the center of symmetry, like what we studied in IR spectroscopy. So this molecule will be having spectra under Raman spectroscopy or rotational Raman spectroscopy. And for these molecules, if we are considering with the center of symmetry, there are two possibilities. Okay? Molecule with without any nuclear spin. That is, this is because of the nuclear spin effect. So the molecule with the center of symmetry. So first we have to consider the center of symmetry. Okay? These molecules, the molecule should have center of symmetry. And if those molecules have a nuclear spin which is equal to 0, or which are having a nuclear spin which is equal to some value. Okay? Let's say some x. Okay? Or they are possessing some nuclear spin value. These two cases we have. Those molecules with nuclear spin equal to 0, those nucleus which will be giving you missing, will be having missing alternative lines in spectrum. And those molecules which are having a nuclear spin and also possessing center of symmetry, then those molecules will be giving you alternating so this we already discussed what is the missing of the line and alternating Raman spectroscopy itself. So for example, if you consider, for example, in this case, oxygen that the oxygen molecule does not possess that the spin value of this oxygen is equal to 0. So in that case, for example, for oxygen case, J equal to even number of J values are missing, so which means that J equal to 0, J equal to 2, 4, etc. All these values, all these lines are missing. Okay. All other values will be present. So which means that if you consider the rotation spectra of oxygen, okay, so those J equal to 0, this first line is J equal to 0. So this one will be rotational spectra. We are considering this for oxygen. And what will happen is that this line will be missing, this line will be missing, and this line also will be missing. This line will be missing. And only these other lines which are present, this odd number of J values, this will be present, this will be present, this will be present. So that is in the case of the molecule with nuclear spin 0. And in that case, remember that in that case, the separation between the lines, what will happen to those separation between the lines? This line separation will become 8. Will become 8. So in some questions, for example, in CSIR also, maybe in some questions it will ask oxygen, what is the p value corresponding to oxygen with, or what is the moment of inertia corresponding to p value that will be given. and you will be knowing what is the rotational, pure rotational lines. And the adjacent lines will be having a suppression of 4B and all those things, and you will directly substitute in 4B. But remember that for oxygen nuclear spin is 0. Okay? Sometimes they may give you in question, but sometimes they will ask directly. So this particular molecule is having nuclear spin which is 0. So then the alternative lines will be missing. In that case, it will become alternate lines will be having a suppression 8B. Remember that. So it will be directly giving, sorry, in this case, it will not give you B value, but it will give you directly the suppression line between, suppression between the lines is given by this number. Okay? That will be. And then you have to take it as 8B instead of 4. That all such kind of questions may come. So I will not be discussing all those. But you have to remember that why, when. Okay, so that's about the nuclear spin effect on your spectra. Because of that nuclear spin, you will be having missing alternative lines. You also have alternating intensity spectra. So why these kind of things are needed? Because if you are having alternating line which is missing in your spectra, which means that your molecule is having a nuclear spin. That is your observation. So if you are making any new nucleus, sorry, new molecule, new molecular structure or something, and you are studying that under this Raman spectroscopy, and we found that the alternative lines are missing, which means that your molecule is having 0 nuclear spin. Okay, if it is alternative intensity, the lines are having alternating intensity, then which means that it is having a center of symmetry, but nuclear spin is not. Okay? But in the previous case, it is having central symmetry with nuclear spin. So you will be getting information about the molecule by studying this. Okay, so that's all about it, and we have one more thing. When for example, when the linear molecule consists of have more than 3 atoms, when the linear molecule consists of more than 3 heavy atoms, then the moment of inertia will be larger. Moment of inertia is larger, and the rotational fine structure, rotational fine structure become rotational fine structure is often unresolved. So what this means that when your molecule is having more than 3 atoms with heavy atoms, okay, more than 3 heavy atoms, which means that your mu is going to get increased. Your reduced mass, this case, mu will be getting increased because mu is nothing but mu1 by mu1 plus mu. So anyway, this product is getting. Okay. So your mu will be getting increased when you are having heavy atoms your molecule. And if you are considering Raman spectroscopy with 3 heavy atoms, more than 3 heavy atoms, more than 3 heavy atoms, then obviously this mu will get increased, which means that your I is also getting increased. That is the moment of inertia will be larger, because your moment of inertia is nothing but mu into r square. So moment of inertia will get larger, it will be larger, and your B is nothing but h square by 8 pi square IC. Okay, so when your moment of inertia is larger, I is going to become larger here. This means that your B is going to be decreased. What is B now? B is the separation between each and individual lines in your Raman rotation Raman spectra. So this will get decreased, means your lines will be very close to each other and will not be able to finish these lines. That's what is called as unresolved. That is the fine structure. Fine structure is nothing but individual lines. And that will become unresolved. It means that individual lines cannot be observed. Right? Otherwise, that the spectra will become continuous lines that more than 3 heavy atoms. But we can often we'll get some different information as compared to the IR and microwave spectroscopy. As we discussed earlier, we can also treat the homonuclear molecules in the spectroscopy, IR and microwave spectroscopy. That kind of advantage is also there. There is one more thing, one more important point is that we will discuss later also. When you are having some lines in which is present in IR spectra, which may have spectra, and if some lines which are present in the Raman spectra, it may be absent in the spectra. So it is like a complementary technique. Some lines which may be absent in IR spectra can be observed in Raman spectra, which means that some samples or some bonding in your molecule which are active in IR, which are inactive in Raman spectra. Similarly, some molecule which are active in Raman is inactive in IR. So we have to take both IR and Raman to get complete picture of your molecule. And this particular process of Raman active and IR inactive, similarly IR active and Raman inactive, called as mutual exchange that we discussed. So okay, so that's all about today's lecture.